Okay, hi everyone. Today I'm going to presentation my research method, which is the topic is a comparative study of CNN vision transformers architectures for plant disease detection. So my name is Wilson Anjulaisan, and today I'm presentation this one. Okay, okay, let's move to the background. Image classification is technology that helps computers understand visual content. It's very useful not only in areas like self-driving cars and medicine, but also in agriculture early. In the past, people used traditional method, but now deep learning has taken over. Okay, there's two main architectures. The first one is CNN, which has dominated the field for the past decade. CNN excels at the recognizing local features such as leaf textures or the age of objects. In the other hand, there is a vision transformers, or VIT, a newer approach. Unlike CNN, VIT divides an image into small pages and uses a self-attention mechanism to understand the relationship between these patches. This approach allows VIT to capture the global context of an image very effectively. Okay, the objective. So the main question is when we use CNN and when we should use VIT. Our goal is to answer this by doing a direct comparison. We're not just comparing the standard CNN and VIT, but there is advanced version like CNN with C-band, which is a CNN with attention module version versus a date. There is a more efficient VIT. We focus on specific case, detecting Apple-escape disease, and evaluate which model performs better in terms of accuracy and efficiency. Okay, now how it works on CNN. Before we move on to methodology, let's understand this a bit deeper. As we can see in the diagram, CNN works by applying filters or kernels to scan the image. First layer detects simple things like edge or corners. The next layers combine these two, recognize more complex shades and so on. This makes CNN very good at understanding fine textures on leaves. Now, how it works on VIT. On the other hand, there's VIT works very differently. It divides an image into several small parts called pages. Then, through the self-attention mechanism, it looks at all the pages at once to decide which one are the most important and how they relate to each other. This allows VIT to understand the global context, such as how disease spreads across the entire surface of a leaf. Interestingly, recent research trends no longer focus on choosing purely between CNN or VIT. Many researchers are now developing hybrid architectures. The idea is to combine the strength of both, using CNN, what is the best, extracting local features, and then passing the result to the VIT, which is a global modeling. This shows that these two architectures can actually complement each other. Okay, here's the workflow of our methodology used in this research, which we'll explain in the next few slides. The process starts with the data collection, followed by pre-processing, data splitting, and model definition, training, and finally we model the model evaluation to measure the performance. Now the dataset and pre-processing. The first step is data. We use a popular public dataset called Plant Village, which is it from Kaggle. However, raw data can be used right away. We apply three pre-processing steps. First, resizing, so that all images have the same size. Second, normalization, to make the training process more stable. And the last one is data augmentation. We randomly rotate and flip the image. This is a simple trick to artificially increase our data so the model can learn better. Now the model and evaluation metrics. Here's the core of our experiment. We're defined two competitors. between CNN CBAM and DATE. We didn't train this model from scratch because that would take very long time. Instead, we used transfer learning, meaning we took models that we already smart, trained on large dataset like ImageNet, and fine-tune them our plant disease dataset. We split the data into two parts: training data to teach the model and testing data, which was kept hidden for evaluation. Okay, next, the expected outcomes. In the study, we aim to accomplish three things. First, identify which model, CNN, CBAM, or DATE, gives the highest accuracy for AppleScape classification. The second one, provide clear recommendation for architect developer on which model to choose based on their needs. And third, explain the trade-off between performance and efficiency so we can see which model is more accurate and which one is more computationally efficient. Here's the timeline and resources. In the first month, we prepared data, collecting the data set and pre-processing the image. In the second month, we set everything up, splitting the data and defining the models. And the third month, we trained the both models. And in the fourth month, we evaluate the result and compare their performance. In the conclusion, to conclude, our study directly compares to the advanced model, which is CNN, CBAM, and DATE. We aim to determine which one performs better for AppleScape detection by looking at the key metrics such as accuracy, precision, and F1 score, while also considering how efficient each model is to train. Our findings are expected to give practical recommendations for agri-tech developers, helping them choose the most suitable model for real-world plant disease detection system. Okay, that's all from me. Thank you.